I'm going to walk you through how to work out these deflection problems. I'm going to use from Chapter 3 problems 36A, 36B, and 36C. So this will also be somewhat of a refresher on those concepts that you went through in Chapter 3. So I've already filled out my givens on that. I put in, for the 836, those givens, the allowable bending stress, the allowable unit stress, and the modulus of elasticity. These will be constant for what we're doing because we're always using that 836 steel. This is the allowable deflection, which is just your length divided by 360. So the equation I have here is this times 12 to convert it to inches divided by 360. So that's as much of how far the beam can bend down before it's out of spec. So I'm going to be moving this green block down to reveal what I got for answers. Go ahead and try to figure them out before I get to that point, and hopefully that'll help you understand this stuff a little better. So for this first beam here, I'm going to switch over to my diagram. Okay. So to solve for our reactions, which we're going to need, let me go back real quick. We're going to need to know those to calculate, to get our maximum vertical shear, which we need that to calculate our unit shearing stress to make sure that that's going to be safe for this particular load for whatever beam we select. Okay, so on these, that's pretty easy. That's just going to be your total load divided by 2, because you're going to need our total load, our reactions need to equal the total load. So since this is uniform, you're going to need the same amount of force on either side, so that's just total load divided by 2, and those are your reactions. You also could go the long way route and say solve about R2, so you have R1, oops, that's a B, R1 times the distance to R2, which is 24, minus our load, which is, what was that, 1,800 pounds, 18,000 pounds, times to the center of it, which is 12, which that's going to give us 9,000, just like that other, just taking the total load divided by 2. Okay. So I'm going to move this down. So our reaction 1, reaction 2 are 9,000, which makes our maximum vertical shear 9,000. On these beams where the reactions are on the very outside edges, your maximum vertical shear is always going to be one of these two numbers. So now we'll calculate maximum moment. Pause it and see if you can figure it out. Okay, so one thing that might help you as you're doing these, oops, keep erasing more than I wanted to, is to start sketching out what the vertical shear diagram would look like. So if I'm looking at this beam here, I got my reaction 1 right here, so that's going to shoot up, and then now it's just distributed load, so that's just going to gradually move down, and then we have reaction 2 again. So that would be the shape of our vertical shear diagram. And as you can see, since it's uniform, we pass through 0 on our vertical shear about at the halfway point of the beam, which is 12. So we can use that 12 foot in our equation to calculate maximum moment. So our maximum moment is, there's a shortcut, which is for something this simple, you could just maximum moment equals little w times length squared divided by 8. Or the long way, you could do reaction 1 times 12 minus our load 1 little w times 12, because that's where we're at on the beam. So this is calculating the weight of it. And then it's always, when you're using the distance on this one, it's always to the center of that section. So that'd be 6. So either of these numbers are going to give you the same answer. So I'm going to put 750 times 24 squared divided by 8, which equals 54,000. That's the same thing if I did this one. That's reaction 1 with 9,000 times 12 minus 750 times 12 times 6, which is the same number. There you go. And that's in foot-pounds, so multiply that by 12, and that gives you your answer in inch-pounds. If you were to put this into SolidWorks, these are the numbers that would spit out as well. The shape of, you could have any shape of a beam when you're trying to solve for the maximum moments in SolidWorks. Okay, so now the next step is the section modulus, which will help us find our limitations, or what type of beam we can select where it would be safe. So section modulus is, let me clear off my workspace here. So that is S equals, section modulus equals our maximum moment divided by our allowable bending stress, which is 24,000. So that would be, what was that number again? 54,000 divided by 24,000. Which is 22.25. But I think I just said that wrong, because that was foot-pounds, we want inch-pounds, so it was actually 648,000 divided by 24,000, which is that number. You can ignore this one for right now. This is me just checking my math. So clicking on that, 648,000 divided by 24,000. In the book, he has the equation for deflection is a constant 5 divided by 384 times your total weight, or big W, times length cubed divided by your modulus of elasticity times the moment of inertia. The moment of inertia is this column on that chart, the IXX. But a better way of going about that is actually calculate for moment inertia by substituting that modulus elasticity times moment inertia with modulus of elasticity times your allowable deflection. So let's write that out. You don't erase that. So once again, that equation was, so this is going to be for moment of inertia equals 5 divided by 384 times, we'll put this all in parentheses, our W, which would be total weight, that, so what was that, 18,000 pounds, times length, which is 24, but we can convert that into inches. So 24 times 12 cubed divided by, another set of parentheses, our modular elasticity, which is 29 million, times our allowable deflection, so D. Okay, so there's that. And if I go back over to Excel here, so there's that equation written out in Excel. And when you calculate that, you'll get 241.32. So now with these two numbers, we can find what beam to use. So I'm going to go over to my chart here, table. I'm going to filter for numbers greater than 241 point something, so I'll just say 242. And then I have a section modulus of 27, so I'll also filter for numbers greater than 27. Okay, so we got pounds per linear foot. This one's good. These are both good. And those are all heavier, so probably go with the shorter one. So we'll pick a W14 by 26, which I do believe I already picked. Yep. And then to calculate your actual deflection is to throw that same equation we did here, but instead we'll substitute this number with this number. So now, as long as this number is, oh, see, I just did it there. There it is. So that's 0.79. So that's less than this, so that beam is good. And the last thing to check for is your unit stress, which is going to be FV equals our maximum vertical shear divided by the beam's height times the beam's web thickness. So that's this number times this number. I'll write that out. So FV, our unit shearing stress, equals maximum vertical shear divided by D, the beam's height, times TW, the beam's web thickness. Obviously throw parentheses around that. So I'll jump back over to Excel and move it down, and that gives us about 2,500 psi, which is less than the allowable of 14,500. That's usually going to be the case, but it's something to always at least check for. Okay, now moving on to the next one. This one's a little more complicated. The loads aren't distributed evenly. There's no uniformly distributed load. They're all concentrated, so our steps are going to be a little different. So once again, if you try calculating these on your own, and then I'll walk you through it. Since we already have, we can solve for reaction 2 a little quicker because we already have the distance to R1 here on those. So our equation for that is going to be, let's go over here. I'm going to hide this, turn that on. So here's our beam. Okay, so solving for reaction 1 or reaction 2, we're going to go about reaction 1. So that's going to be, okay, load 1 times the distance to R1, which is 3 feet, plus load 2 times the distance to R1, which is 8 feet, plus load 3 times the distance to R1, which is 12. And because, okay, let's see how I want to phrase this. Anyways, so then last step is to divide by 14 feet, because that's the distance of R2 to R1. That's our counterclockwise. Counterclockwise needs to equal clockwise. So these forces would push this beam around this point in a clockwise fashion. This one would push it in counterclockwise. So the actual, before we fill it out like this, it would just be R1 times distance to R2 times distance to R1. So that's 14 equals all this. So to get R2 by itself, divide by 14, which is where that dividing by 14 comes from. When you calculate that out, you should get 1057 approximately. And then to calculate for R1, it's as simple as taking your total load, TL, all right. Total load needs to equal your reaction 1 plus reaction 2. So to calculate that, so now we know R2, so we can subtract R2. So that's total load minus R2 equals R1. And that's, go ahead and calculate that, and you should get 643. Those two together need to equal, as I just said, need to equal your total load. So that plus that plus that equals true. So we're good there. Okay, so kind of like we did on that last time, quick, see if you can sketch out what the vertical shear diagram will look like. So I'll show you that. Okay. So once again, we got a reaction 1 here, so that's gonna move up. And then there's nothing, 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 nothing. And then at 3 feet, it's gonna go down. But this is 600, what was it, 643 and 1057. 43, 1057. So it's going over, it's going to subtract, now it's down, so it's going to move down 400 pounds. So that's not enough to go over to 0. So it's going to go over and over. And now it's going to subtract 500, so that's going to go, I got a line here, that's our 0. At that point, we can tell that that passes through 0. It'd go over, go down again, go over, and then go all the way back up when it hits reaction 2. So that'd be approximately what our vertical shear diagram would look like. So we can tell that at 8 feet it passes through 0. Which, if you want to do that mathematically, you can check each of these points. So at, say, 3 feet, you'll say 3 feet minus and 3 feet plus. Minus meaning not including the 400 pounds, plus meaning including the 400 pounds, so that would just be, at 3 feet, it'd just be R1. At 3 feet plus, it'd be R1 minus L1, which doesn't equal 0. So next one major point would be 8 feet minus and 8 feet plus. And that would be R1, that'd still be R1 minus L1. And at 8 feet plus, it'd be R1 minus L1 minus L2. And at that point, once you know 0, you can keep going. You don't need to really solve the rest of it. Okay, so now we know that it passes through at 8 feet, which you can see here. And now to calculate, so once again, so maximum vertical shear, that's the larger of these two numbers. And then to calculate our maximum moment, we go about 8 feet. So give that a shot on your own. And I'm going to erase some of this. Okay, so maximum moment, M equals, so we're right here. We got R1, looking to the left, times how far away R1 is, which is 8 feet, minus load 1, and then how far away it is, which is 5, because that's 8 minus 3. So it's 5 feet away. So when you calculate that, you should get 3,142.9, and then multiply that by 12, and you'll have 37,714. With that, we can calculate our section modulus, which was S equals maximum moment divided by FB. So go ahead and calculate that. You should get 1.57, as I have here. And then to calculate our moment of inertia again, that was that, oops. That equals the constant 384, 5 divided by 384, times our total load, big W, so that's this number plus that number, times our length, which is 14, times 12, because we want to convert it to inches. That's cubed, and then all that, parenthesis, our modulus elasticity, 29 million, times our allowable deflection, D, and then close my parentheses. So go ahead and calculate that out. Your allowable deflection, once again, is your length converted to inches divided by 360. And once you put that all in, you should get 13.57. So now we have our section modulus and we have our moment of inertia. We can come over here, click on this, change our number filter greater than 13, so I'll just raise it up to 14. And then I will change this one greater than 2, or yeah, 2, and okay. And I think I clicked on, did I get the, oh, wait. Should be I'm gonna just clear filter. Let's try this one more time. Okay. So that okay. Yeah, okay. Greater than 14 and greater than 2. Not sure why that wasn't showing up before. yeah, so I picked this one because that's got the lightest weight and it passes those two numbers. And then to calculate actual deflection, once again, it's just taking the same equation but swapping this number out, your allowable deflection, for the beam's moment of inertia, the 16.4. So after we do that, we can see that this number is less than that one, so the beam is good. And then the last step, check for shear, which that is FV equals maximum vertical shear divided by D, the beam height, times TW, the beam's web thickness. Go ahead and calculate that. So once again, that's V right here times D times TW. So 5.9 times 0.17. On the assignment, I have AW, which AW equals D times TW. So that'd be V divided by AW. And when you do that, you should get 1054, which is less than this number, so the beam is good. Alright, now the last one. I'm going to go, so I filled out everything. Go over here. Hide this, turn that on. Okay, so now I have a distributed load and a concentrated load. So we're going to calculate our reaction 1 and 2. I'll go about, this is at 10 feet. So I'm going to calculate for R2. Once again, it's that clockwise motion. Clockwise needs to equal counterclockwise. So your loads are going in a clockwise motion around R1, and your reaction 2 is going in a counterclockwise. So that's R2 times the distance to R1, which is 18, equals load 1, big W, that's the distributed load, times the distance to R1, which is the halfway point of the beam, because the distributed load spans the entire beam length. So that's that number times 9 plus our 12 kips, or 12,000 pounds, which we'll want to use that number in our equation, times the distance to R1, which is 10. Get R2 by itself, divided by 18, divided by 18. So go ahead and calculate that out. You should get 8,467 approximately. And then to calculate reaction 1, it's just your total loads minus R2, or to draw it out farther, because your negative forces need to equal your positive forces, so R1 plus R2 equals total load. We don't know R1, so subtract R2, put that there, R2. So R1 equals total load minus R2. So go ahead and calculate that, and you should get 7,133 approximately. So now let's do sketch out our vertical shear diagram again. Okay, so we got reaction 1, so it goes straight up. Now we got distributed load, so it starts going gradually down, and about 10 feet we got a concentrated load, so it'll shoot straight down and then start going gradually down again until we get to the end, and then shoot back up because of reaction 2. So I would check your math on this to make sure. So we know at 10 feet we gotta check our math to see that that would be the case, that it would come down here and then shoot down through 0. If this got moved over, eventually this gradual incline could pass through 0. In that case, you'd have to use some algebra to calculate that out. But in this case, it actually is at 10 feet, because if we go, so vertical shear at 10 feet minus versus 10 feet plus. So at 10 feet minus, we have reaction 1 to the left minus 10 feet of this distributed load. So that's load 1 little w times 10 to calculate how much that weighs. And if I were to do that, because wait, let me write this stuff down. 8,484.67, 71.33. I don't really need 84.67, 71.33. So 8,067 minus 200 times 10 equals 6,467. And then if I were to, from that number, now at 10 feet plus, we'd just subtract 12,000 pounds, which that is obviously going to send us through 0. So now we know at 10 feet, vertical shear equals 0. It passes through 0. So I calculated all that. Did I use? Yeah, I used the right number. Okay. Oh, that's right. Reaction 1, 7,133. Either way, it proved that it went past through 0 at 10 feet. So picking a maximum vertical shear, so which one of these numbers is the largest, which is the 8,467. Now we'll calculate our maximum moment about 10 feet. So I'm going to jump back over here. Okay, so M equals, we're at 10 feet, R1 times the distance from this point to there is 10 feet, so that's R1 times 10, minus, all we have to the left of this point is this distributed load, so that's L1 little w times 10 to calculate the weight of it. And then to the distance of it, we're always going to the center of that section, so then that's 5, because 10 divided by 2. And that's it. That's because that's all we have to the left of this point. So go ahead and calculate that. And you should get this in feet-pound times 12 to get this in inch-pounds. Okay. Now to do section modulus. So that's S equals M over FB, which is the 24,000 PSI. So go ahead and calculate that. You should get 30.67. And then let's calculate our moment of inertia. I'll do that one more time. So I equals 5 divided by 384 times our weight, our total load, times our length, which is 18, which that's in feet, so times 12 to convert it to inches, parentheses, and that's cubed divided by our modulus of elasticity, 29 million, times our allowable deflection, which is our length divided by 360. So go ahead, punch those numbers in, and you should get 117.65. We'll come over to our chart table. I'm going to clear my filters. I'm going to go greater than, let's just say 118. Filter greater than 31. Okay, so we got an W835 or W1030, but then there's this 1226, so that's going to be our lightest one. So move that down. I picked a 1226. Calculate your actual deflection. Just replace the same equation here. Just replace your allowable deflection with your moment of inertia. So on this case, that'd be 204. Once you do that, you should get 0.35, which is less than 0.6, so that's good. Then calculate your shear, which once again, that is FV equals maximum vertical shear divided by, as I said, it's either at AW, which is your beam height times web thickness. So AW equals D times TW, which is on the chart. D times TW. So vertical shear divided by D times TW. Move it down. It's 3012, and that's less than that number, so the beam's good. With all the previous assignments, you can use SolidWorks to check your work. Some of these numbers are not going to be exactly the same. This one should be pretty close. This one I'm not always getting the same out of SolidWorks, but your maximum moments and your shears, you can get basically the same numbers out of that one. So, good luck.